Okay, let us now proceed to the sample problems. Sample problem number 1. Find the components of the given force. So we have the given force in here, whose magnitude is 600 pounds. And the direction angles with respect to the positive reference axis. Okay, so this is now the figure. So the force F is directed from A to B. So first, let us try to determine the X, Y, and Z components. Okay, that is now your components, okay, of the position vector AB. Vector AB. Okay, before we can determine the components of the position vector AB. Let us try to determine first the coordinate of point A. So from the figure, so coordinate of point A. So from the figure, this is the x-axis. So your x-coordinate in here is equal to 0. So the x-coordinate is equal to 0. So let's try to determine now the y and z coordinate. Now, if you try to look at this triangle in here, this is the triangle. So we now have, this is 3 feet, and then this one in here is 60 degrees. So we have the y coordinate, this is the y coordinate, and this one in here is the z coordinate. So that is your z coordinate. So your y in here is equal to -3, that is sine of 60 degrees. That is sine of 60 degrees. Now, why negative? Because this is to the left of the origin. And this is therefore equal to -2.598 minus 2.598 feet. Okay. And the z coordinate is now equal to, so this just simply equal to cosine of 60 degrees is equal to z all over 3. And therefore, your z is equal to 3 cosine of 60 degrees. And this is therefore equal to 1.5 feet. So it's equal to 1.5 feet. Now, the coordinates of point, we now have the coordinates of point B. So the coordinates of point B, so your x is equal. So that is now your x coordinate, and that one is equal to 5 feet. And your y coordinate is this one, and the y coordinate is equal to, so we have 1.5 feet. And your z coordinate in here is now equal to, so the z coordinate is equal to 0. So we now have the coordinates of points A and B. So we are now ready to determine the x component of the position vector y, the y component of the position vector AB, and the z component of the position vector AB. So to determine the components of the position of a position vector, so it should be the okay, so we now have the components. Therefore, of the position vector. So we have the position vector, okay, is equal to the coordinates of the head of that position vector. Okay, so I'm just going to place it in there now. The head of the position vector minus the tail of the position vector. So that is now the tail of the position vector. Okay, so we have the head. So we have your x component is equal to xb minus xa. So that is now the coordinate of x at point B minus the coordinate of x at point A. So we have therefore, okay, 0 minus 5. So that is equal, B is 5 minus 0. So that is equal to 5 minus 0. So that is equal to 5. Then we now have the y component. So the y component is now equal to yb minus ya. And yb is equal to 1.5 minus ya is negative, minus and minus 2.598. And this is therefore equal to, okay, so we have equal to positive 4.098. It's 4.098 feet. And the z component of the position vector AB, so we have now the z component is now equal to zb minus za. So your zb in here is equal to 0 minus the z component, which is equal to 1.5. Hence, the z component is equal to negative 1.5. Is equal to negative 1.5. Okay, now from the equation, so from the equation, d is equal to the square root of xb minus xa squared plus, we now have yb minus ya squared plus zb minus za squared. Let's try to determine now the magnitude of the distance d, and this is therefore equal to the square root of 5 squared, and then we have 4.098 plus 4.098, so that is square, and then plus, okay, so the square of the negative is positive, so I'm just going to place it 1.5 square, and therefore your d in here is now equal to 6.637 feet. Okay, so that is equal to 6.637 feet. Now, knowing now the magnitude of the position vector, which is equal to 600, then let us try to express this one. Okay, so let us try to first express this one in its vectorial form, or in the standard Cartesian form of a vector. Okay, so from, this is therefore again, so from, so this is the vector f, this vector is now equal to the magnitude of the vector, which is equal to f, and then we now have your XA, so we have XB minus XA, so that is XB minus XA, and then so we have to place it under now your I. Okay, so we have plus YB minus, so it is YB minus YA, and then that is now your J. Okay, multiply this one by a unit vector J, which is in the direction of the positive y-axis. And then we have plus, we have your ZB minus ZA, multiply this one by a unit vector in the direction of the positive z-axis, which is equal to k. Now, let us try to divide this one. If you try to divide this one by d, and your d in there is now equal to the square root of xb minus xa squared, okay, plus we have your yb minus ya squared plus zb minus za squared. So if you try to simplify this one, let's try to simplify this one so that we will not be writing always in this manner. So the vector f is now equal to the magnitude of that vector. So the magnitude of that vector, multiply this one by. So your xb minus xa is now the x component. So that is now your x component. Okay, multiply this one by a unit vector I. Plus yb minus ya is the y component. Multiply this one by a unit vector j. Plus zb minus za is the z component. So that is now z, multiply this one by a unit vector k. Okay, so we now have all over. So the square root of xb minus xa squared plus the square root of yb minus ya squared plus zb minus za squared is now equal to d. So that is now equal to d. So in other words, this is equal to the vector f. Okay, so we now have, in other words, we have now the vector f. So the vector f is now represented as the magnitude all over the magnitude of the distance d. We now have xi plus yj plus zk. You try to take note that your x, y, and z in this equation are the components of the distance d, which this component again of the distance d can be determined by subtracting the coordinates of the tail of the vector from the head of that vector. So let's try to determine now in vectorial form. Okay, so your f in here is now equal to, so the magnitude of the position vector f directed from point A to point B is 600 pounds. So that is 600 pounds. Let's try to divide this one by d, and your d is 6.637 feet. So we now have your x component. So your x component is 5. So that is 5i. Plus your y component is 4.098. 4.098 j. And then plus your z component of the distance d is negative 1.5. So that is negative 1.5 k. So this is now your vector f in its standard Cartesian form. So let us try to determine now your x component of the vector, the magnitude. So your fx in here is now equal to, since this is a unit vector in the direction of the positive, I is a unit vector in the direction of the positive x-axis. So we have fx I plus fyj plus fjk. So that is all over d. So this is equal to 600 all over 6.637. Multiply this one by 5. And the x component therefore is 452. So we have 452.011 pounds. So your Fy in here is now equal to 600 all over 6.637. Multiply this by 4.098, and this is equal to 370 points. So that is 370.469 pounds. And the component of the position vector AB directed from A to B in the Z direction is equal to 600 all over 6.637. Multiply this one by negative 1.5, or that is equal to negative 135.603. So that's 135.603 pounds. Now, let us try to determine now the direction. So we now have the direction angles or direction cosines. Okay, so the position vector having a magnitude from point A to point B, having a magnitude of 600 pounds, makes an angle theta x, which is equal to the arc cosine. So that is now the arc cosine of fx all over f. So this is therefore equal to, your fx is equal to 452.011 divide this one. We have, okay, so we have the arc cosine. So this is now the arc cosine of 452.011 all over 600. And this is therefore equal to 41.12 degrees. Theta y is now equal to the arc cosine of fy all over f. So that is equal to the arc cosine, and fy is 370, that is 370.469 pounds all over 600, and theta y therefore is equal to 51.87 degrees. And theta z is now equal to the arc cosine of fz all over f. So we have the arc cosine of fz is negative 135.603 pounds all over 600. 100 pounds. Hence, your theta C is equal to 103.06 degrees. So this is now your sample problem number 2. Now the slope of the 7.5 kilonewton force is specified as shown. So we have 5 vertical to 12 horizontal. Express this force in Cartesian vector form. Okay, so first, let us try to determine the distance D, or the hypotenuse of the slope triangle. So that is your 5, and this one is now your 12. So that is the hypotenuse of the slope triangle. So your D in here is now equal to the square root. We have 12 square plus 5 square, or this is equal to 13. Next, let us try to determine the x and y component of the force F equal to 7.5 kilonewton. So we have the x component. So that is therefore the x component. So that is now your f of x. So your f of x is now equal to the force multiply this one by the horizontal slope all over the hypotenuse of the slope triangle, which is equal to 13. And this is therefore equal to 7.5 multiply this by 12 all over 13. And this gives and this is equal to 6.6923 kilonewton. So that is going to the left. So I'm just going to indicate this by an arrow. So that is going to the left. So your y component, f sub y, is now equal to. So this is now the component in the y direction. So we have your f of y. So that is equal to f. Then we have the vertical or the y slope, which is 5 all over your d, and that one is equal to 13. Or this is equal to 7.5 multiply this by 5 all over 13. So this is therefore equal to 2.885 kilonewton. 2.885 kilonewton, and this is downward force. Now, knowing now the x component and the y component of this force having a magnitude of 7.5 kilonewtons, we are now ready to express this one in Cartesian vector form. So in Cartesian vector form, your f, so this is the vector f, is now equal to, this is therefore equal to, we now have fxi plus fyj. So that is fxi plus fyj. This because this is only a two-dimensional force system, but we are just expressing this one in the standard Cartesian form of representing a vector. Okay, unlike in the previous example, it is a three-dimensional force system. That's why we only have x and y. So we only have x and y. So at this point, then now, let's try to recall first so that you will know where this equation came from. Okay, so previously, we have a vector f is now equal to your f all over d multiply this one by xi plus yj plus zk. Now, so you try to take note in here now that we only have to get this one because this is a two-dimensional force system. And therefore, your f in here is now equal to f all over d multiply this by xi plus y xi plus yj. So your f over d multiply this one by x is the x component, okay, as what we have told before. So your is equal to the x component. So your f of x in there is equal to f all over d multiply this one by x. So your x therefore, so multiply this one by x, and your f of y is equal to f all over d multiply this one by y. So in other words, your f therefore, f over dx is now your f of x. And then f over dy is now your f sub y. Okay, so you have your I, and that is now your j. And this is therefore the vector f, or the force f in its standard Cartesian form. So the vector f in here is now equal to, so your fx is 6.923 kilonewtons to the left. Okay, so to the left is negative. Okay, so from your sign convention, forces going to the right is positive and forces going to the left is negative. And forces going upward is positive and forces going downward is negative. Since the component in the x-axis is going to the left, so we have negative 6.923 I. And the component in the y-axis is going downward, so we also have negative 2.885 J. Okay, so this one is in kilonewton. Okay, sample problem number 3. Now, the line of action of the 2,500 pounds force is directed from point A to point B. Determine the x and y components of the force and express it in Cartesian form. So we have the x, all coordinates in here are in meters. So you have x that is in meter, y is in meter. So the coordinate of point A is negative 7 and negative 2. Coordinates of point B is positive 8 and positive 6. So first, let us try to determine the position vector r. So how are we going to determine again the position vector r? So the position vector r now let us try to determine first the components of the distance d. So we have your x component is equal to, so we have again head coordinate, coordinates of the head of the vector to the tail of the vector minus the coordinates of the tail of the vector. So we have 8 minus and minus. 8 minus and minus 7. So that is equal to 15. And then we now have the y component of the position vector r is 6 minus and minus 2. So 6 minus and minus 2, or that one is equal to 8. That is therefore equal to 8. So the position vector r directed from A to B is now equal to, that is, xi plus yj. Hence, the position vector is now equal to the x component, which is equal to 15. I plus, we now have your 8j. It's now your 8. Let's try to determine now. So if you try to determine, okay, the magnitude of the position vector r, magnitude of the position vector r. So the magnitude of the position vector I, vector r is equal to, okay, r not written in boldface. So this is therefore equal to the square root of the x component square. So it's the x component square, okay, plus the y component square. And this is therefore equal to the square root of 15 square plus 8 square. So this is equal to 17. So that is equal to 17. Now, let us try to express this force F in its standard Cartesian form of representing a vector. So you try to recall, okay, that if you have a force F, so this is now the vector F is now equal to, okay, if you try to recall this one, this vector F is equal to its magnitude multiply this one by a unit vector r, and that unit vector r is now the position, okay, the unit vector r. Okay, so this is, now you try to take note in here now that the position vector is directed along the line of action of the force. You try to recall what we have last, okay, when we discussed your position vector along a line, okay, and that of your unit vector. So your vector is Cartesian form is now equal to the magnitude of the force multiply this one by a unit vector r. So that is now a unit vector r. Now you try to recall that a unit vector r is now equal to the position vector r all over the magnitude, which is equal to, written in r, not in the boldface r. Okay, so that is a unit vector, definition of a unit vector. So that the vector, the force in its Cartesian form, is now equal to, okay, the magnitude of the force is 2,500 pounds. Let's try to multiply this one by the position vector r, which is equal to 15I plus 8j all over the magnitude of the position vector r, which is equal to 17. That one is now equal to 17. Hence, so this is, okay, so this one in here is now equal to, so 2,500 times 15 all over 17 is 2,205. Okay, 2,205.882 I. So we have 2,500 times 8 over 17 is 1176.471 J. Okay, so this is the standard Cartesian form of the force 2,000 having a magnitude of 2,500 pounds. So hence, we now have your x and y component. Again, you try to recall again that the vector f is now equal to fxi plus fyj. So fx therefore, which is now the component, is now equal to 2,205.882 pounds. And your Fy is now equal to, so that is 1176.471 pounds. Sample problem number 4. Find the rectangular representation of the force F shown given that its magnitude is 750 newtons. So this is now the force F, and the magnitude of F is equal to 750 newtons. And determine the unit vector acting along its line of action. So the unit vector acting along its line of action. So first, let us try to determine the coordinates. Okay? Coordinates of point A. So the coordinates of point A, X, Y, and Z. So the coordinate of this is the x-axis, this is the y-axis, and that one is the z-axis. So the coordinate of point A in the x-axis is 4 meters. That is 4 meters. The coordinate in the y-axis of point A, okay, so that is equal to 0, and your z at point A is equal to 3. We now have the coordinates of point B. So you have your x, we have your y, and that one is now your z. For B, x is equal to 0, y is equal, so x is equal to 0, your y is equal to 6, and your z is equal to 0. So that is therefore the coordinates of points A and B. So I'm just going to write the coordinates of points A and B. Okay, so for points A, 403, 403. And then for point B, it is 060. 0, 6, 0. Now, let's try to determine now your x and y components. So let's try to determine your x and y component. Okay, so your x components is now equal to, so that is, we now have head minus tail. So we have 0 minus 4. So that is 0 minus 4. So that is negative 4. And then we now have your y component. So that is head again minus tail. 6 minus 0. 6 minus 0. So that is positive 6. And then your z component, we have head minus tail again. 0 minus 3. So 0 minus 3. And that is equal to a negative 3. Okay. 3. So, let us try to express the force in Cartesian vector form. So, you have to express the force in Cartesian vector form. So, first, let us try to determine the distance. You try to determine the distance d of AB. So, the distance d of AB, the magnitude of the distance d, which is equal to the square root, okay, of negative 4 square, so that is positive, negative, plus 6 square, negative square is positive, plus 3 square. And therefore, the distance d of AB, or length AB, is now equal to 7.81 meters. So that is 7.81 meters. Now, let's try to, you try to express, now, express the force F. The force F with magnitude 750 newtons in Cartesian vector form. In Cartesian vector form. So this is therefore equal to, okay, so the vector F is now equal to the magnitude, which is now your F, multiply this one by a unit vector in the direction AB. A unit vector in the direction AB. So we're going to determine now the unit vector in the direction AB. So this is therefore equal to the position vector AB. So this is the position vector AB all over the magnitude of this position vector. So the position vector AB is now equal to, this is therefore equal to, so we have the x component I, you have the y component j, and you have the z component, okay, k. So this is equal to, so your x component is minus 4i plus you have 6j minus 3k. And your r in here is now equal to the square root of your x, which is 4 square plus, we have your 6 square plus 3 square. And this one is now equal to 7.81. So it's equal to 7.81. Hence, the vector in its Cartesian form is now equal to, so the vector in its Cartesian form is now equal to F is 750. That one is 750 newtons. So your R, the position vector in the direction AB, is minus 4I plus 6J, and then minus 3K all over the magnitude of the position vector in the direction AB, which is equal to 7.81. Hence, the force in its Cartesian vector form is now equal to, this is now equal to 750 times 4 over 7.81, so that is equal to 384.123 I plus 750 times 6 over 7.81 is 576.18 J. And then 750 times 3 over 7.81, so that is minus, so we have minus 288.092K. So this is therefore the standard Cartesian form of the 750 Newton force. Determine the unit vector acting along its line of action. So if you try to recall that the unit vector acting along its line of action is now equal to, so we have your R AB all over the magnitude of R AB. So this is your RAB, okay, you go back, your RAB in here is equal to minus 4I plus 6J minus 3K. And the magnitude of this, okay, the magnitude of this vector acting along its line of action is equal to 7.81. So it is equal to 7.81. Hence, the position vector along line AB is now equal to, so there is now the position vector along line AB is now equal to, okay, 4 over 7.81. 4 over 7.81 is negative 0.512I. 6 over 7.81 is 0.768. That is now your J. Minus 3 over 7.81 is 0.512 3, 8, 4, K. So this is the vector along line AB.